Welcome to the second video of the Electricity Magnetism unit. Today we're going to be looking at concepts of electric field strength and electric potential energy. Hopefully you remember that an electric field is a region where a charged object experiences a force. You'll also remember that when we draw an electric field, we can represent the strength of the field by the distance between the field lines. Which means the electric field around this point charge is strong near the charge, and it gets weaker as we get further away. If we take a uniform electric field like this one, between this positive plate and this negative plate, and we put a negative charge in it, it will experience a force in the opposite direction to the direction of the electric field. If we put a positive charge in, it will experience a force in the same direction as the electric field. But what's going to affect the magnitude or the size of these forces? There's two things that can affect the size of these forces. Can you think what they might be? The two things that affect the size of the force are the charge of the particle. If there's more charge, there will be a greater force. And the other thing that will affect the force on the charged particle is the field strength. If we increase the field strength, we'll also increase the force on the charged particle. This leads to the equation force equals EQ, where force is the force on the charged particle, E is the electric field strength, and Q is the charge of the charged particle. We can see that force is directly proportional to the field strength. We can also see that the force is directly proportional to the charge. We can rearrange this formula and get this formula. Which gives us a formula for the electric field strength. Since we know the units for force are newtons, and we know the units for charge are coulomb, we've now got some units for the electric field strength. The units for the electric field strength are newtons per coulomb, or newtons per coulomb. The electric field strength, it's a vector, which means it has both a magnitude and a direction. Remember, we represent the direction with the arrows and the magnitude with the spacing between the field lines. The direction of the magnetic field is the same direction as the force if the object is positively charged. So now we have a way of measuring electric field strength. What can we do with this newfound ability? Hopefully you remember from your previous physics training that if you lift an object in the Earth's gravitational field, it gains gravitational potential energy. By lifting the object, you're doing work, which simply means you're converting energy from one type of energy to another. If you let go of the object that you've lifted up, its gravitational potential energy will be converted into kinetic energy as it falls. The work you do in lifting the object up is equal to the force that you overcome, which is the weight of the object calculated by multiplying its mass by the gravitational field strength, G. You probably know G as gravity. This little g actually stands for gravitational field strength. Where was I? That's right. Calculating the gravitational potential energy. The amount of gravitational potential energy that mass has is calculated by multiplying the force you've overcome by the distance that you've lifted it. In this case, it's the height that you've lifted it. So, the amount of work you've done, or the amount of energy you've transformed, delta E, change in energy, is equal to mg, for the weight force you've overcome, times the height, or the change in height. A charged particle in an electric field will behave much the same way as an object with mass in a gravitational field. If you move this charged particle towards the positive plate, you need to do some work. You need to overcome the force on that charged particle. We saw earlier that the force on the charged particle is equal to the particle's charge times the electric field strength. Particle's charge times the electric field strength. And if we know the distance that we move it, say from here to here, let's call that x, the work done, or the amount of energy transformed, delta E, is equal to the force overcome times the distance moved. This delta E, or the work done, is the electric potential energy stored in the electric field. Notice the difference between energy E and electric field strength, with the tilde under it to represent the electric field. If we let go of this charged particle here, it's going to accelerate away from the positive plate towards the negative plate. It's going to convert its electric potential energy into kinetic energy, just like if we let go of this massive object. It's going to convert its gravitational potential energy into kinetic energy as it accelerates towards the Earth's surface. In lifting a mass, the gravitational potential energy is stored in the gravitational field. In lifting a charged particle against the electric field, the energy is stored in the electric field. We can show the different types of energy by using subscripts. delta E here is GP, EGP, gravitational potential energy. Over here we can use EP for electric potential energy. That's it for today. So let's sum up. The forces on a charged object in an electric field are proportional to the charge of the object, Q, and also proportional to the electric field strength. That gives us the formula F equals E Q. We rearranged this formula to get another formula to show the electric field strength. Electric field strength is equal to force divided by charge. From this, we found that the units for electric field strength are newtons per coulomb. We also saw that electric potential energy is the amount of energy gained or lost by a charged particle moving in an electric field. If it goes in the same direction as the force on that charged particle due to the electric field, it loses electric potential energy. If it moves against that force, and you have to overcome that force, then you're doing work, and it has to gain electric potential energy. And the amount of electric potential energy gained is equal to the force overcome, which can be calculated by multiplying the electric field strength by the charge of the particle and multiplying it by the distance that that charged particle moves. We usually call this distance x. So the electric potential energy stored in the electric field is equal to the electric field strength times the charge of the particle moved times the distance that that particle moved. And because electric potential energy is an energy, like all other energies, it is measured in joules. Don't forget to write down questions and review this video, and check out another link below for another interactive simulation looking at charged particles in electric fields.